All right, guys, welcome back. So last time we learned about latitude and longitude in detail, latitude of New York State, longitude of New York State. Today we're moving on to a slightly different topic. We're learning about field lines today, field maps. And if you look at this particular map right here, you'll see there's a bunch of lines that kind of circle around that point X. And they move outwards, and they have labels on them, 1 hour, 2 hours, so on and so forth. What might these lines represent? Take a moment, think about it. There's a key word here. Some of you might recognize that word having to do with earthquakes. Well, these aren't earthquake waves. These are actually ocean waves. This is a map of a tsunami that occurred in 2004, I believe it was, right after Christmas. And these show how long it took for the tsunami waves to go away or travel away from the epicenter. So these types of maps are useful for many reasons. They tell us information that we might want to know. Let's look at the second map here. Average yearly precipitation in inches is what this map is titled. What can you learn by looking at these lines? You can see the numbers are different everywhere. We're somewhere in this area here, 44 and 40, 48, 52, 52. Ooh, look at this down here, 56, 60, 52. This wide space right here. Well, later on in this topic, you're going to learn that not only can you learn distance or actual amounts of precipitation from this map, but you can learn gradients, which are really, in this map, how closely packed the lines are, showing big changes over short distances or not much change over big distances. Reading field and topographic maps is today's lesson. Before talking about topo maps, you first must understand what is meant by a field. Fields are regions of space where you can measure a value at any point. Kind of like, a soccer field or a football field has a grid on it. But there's also other fields, force fields, magnetic fields. But we also create fields in the earth sciences, or geography actually, to represent the surface of the earth. But there are other fields too. We're going to learn about temperature fields, air pressure fields, glacial elevation fields. Elevations of the land is a big one we're going to be doing this unit. And of course, we might want to draw these field maps just to learn about the type of field that is being measured. There's lots of things you can learn about it. Many of these fields are dynamic. They're constantly changing, so the numbers change as well. Now, elevation fields don't change very fast usually. It takes a long time for the land to erode down or to build up. But other fields, like a temperature field, might change very, very rapidly from one day to the next. You'd have a hot day and then a cold day the next day. Let's take a look at this field right here. What's it telling us? So we have some information at the bottom here. It says it's an island. It says that the elevations are in meters, and the O stands for ocean. There's a distance scale, and north is up. That's our legend down there. So here's the ocean. And this is our island. And this must be some other piece of land, maybe the mainland. And if you look at the map itself, we can see that the island doesn't have the same elevations in all the spots. They're all different. And the highest part of the island you can see is near point A at 135 meters in elevation. Now, the lines that we're going to learn how to draw are called isolines. These lines help us visualize the field, and they're drawn connecting equal points of value. Here are some examples of isolines. Lines that connect lines of barometric air pressure, a meteorological term, These lines are called isobars. Isotherms connect lines of equal temperature. Contour lines, which we're going to be doing the most of, connect lines of equal elevations. And there's some other terms too. Isohyates connect equal points of rainfall or precipitation. It could be snowfall. And there are others. We're not going to get into too many of them. We'll keep it limited today. So here's a field. Where's the heat source? Well, it's pretty obvious if you look at the numbers, look for the highest temperature, that the heat source is somewhere in this area of the room. So maybe there's something there, like a kid with a fever, or maybe there's an overhead machine that's giving off heat, or something like that. Or maybe a heater duct or something. But you can definitely learn something about that room by looking at the temperatures. This particular field is a map of pollution. These numbers represent pollution in parts per billion, ppb. And you can see that if you were asked, where did the spill most likely happen of pollution? You'd probably say somewhere in this area. So there is a use for these types of maps. You could even ask the question, well, why does the pollution seem to be spreading this way? What could cause that? Should we warn the homeowners in that area if it's polluting that way? And why is it not going as much in these areas? And there are many reasons for this. You could probably come up with one right now. On this particular map showing rainfall, where would the 25-inch rainfall ISO line go? And if you look at the map, you'd have to find numbers that are higher than 25 and lower than 25. And I actually see a 25 up here. So I'm going to draw my line going from here through numbers that are both larger and smaller, kind of like this. You're allowed to go off the map. And over here, I'm going to have to go between the 23.44 and the 28.83. I'm going to go closer to this 24 over here than that 29. And I would probably run it off the map somewhere over here. And then label it 25 inches. So that is an ISO line that shows a certain type of rainfall. But everywhere on that blue line has the same amount of rainfall. That's the point of an ISO line. Connect points of equal value. This particular map says, starting at 20 meters, draw isolines at an interval of 2 meters. So we got to go by twos. Each of the measurements shown is an elevation above sea level in meters. So I'm going to start at 20. I'm going to find my 20. I see some 20s over here. And I'm going to start off the map. And I see a 19 and a 21. I got to go right between them. And I'm going to go to 22s. And off the map, 24s. And off the map, 26s. Ooh, this one's tricky. Ooh, what do I do? In this case, I think I might loop it back around, something like this. And then we seem to be decreasing back down from 26 to lower numbers. And there's 3 22s here, so I actually might make a loop. You could do that. Or there's another option. It could be a line that comes in here and goes like that. Either way is technically correct. Now the last thing you should do on all your isolines is label what they are. So this is a 20 meter line, 22 meters, 24 meters, 26 meters, back to 24, and 22. Okay, so now we understand isolines on field maps. I wonder how you could tell how steep a slope is or how much temperature change occurs between 2 points in a room. Well, this is called gradient. Gradient is the average slope or steepness of change between 2 points in a field. There is a formula in your reference tables for gradient. It's right on the front cover. It's It's the change in the field value over the distance between the 2 points. The field value is the other number besides distance on the map, and you'll see that once you get to some examples. Here's a simple one. It's not a picture problem, it's a word problem. The elevation of the summit of Mount Marcy is 5,344 feet above sea level. 7 miles later, it drops to 2,300 feet in elevation where the mountain levels off to flat land. Find the gradient. So first, you write down the formula. Change in the field value over distance is gradient. Second is our substitutions. You notice on the bottom we have our distance number. The bigger unit number is distance. The top, we want to find the change in the field value. Now change means we're going to be subtracting the bigger from the smaller elevation. That comes out to be about 3,044 feet divided by 7 miles, and the answer comes out to be 434.9, and you have to have units on these guys. The top unit was in feet, the bottom unit was in miles, and when you divide feet by miles, you get feet per mile. A lot of people don't know what this little slash means. It's just the divide sign. If you just flip this, rotate this whole thing a little bit like this, it would be feet over mile. Here's another example. The elevation of the Canigere Creek is roughly 600 feet above sea level at Wintergreen Park. 2 miles later, it drops to 300 feet where it enters the Mohawk River. Find the gradient of the creek between the park and the river. Now I'm going to pause the video here, and you guys are going to try this all by yourselves.